And this is one of my heroes of chemistry, AP de Silva, who based at Queen's University, Belfast. He is Sri Lankan in origin and worked in Belfast for many, many years. Good friend of mine. And what he did was took some of this basic cation binding chemistry and made some sensors for blood electrolyte that were simple and cheap and elegant and beautiful. I admire this work so much. What did he do? Well, he took a design. This is an R, an F, and an S. What do each of these things mean? The R is a receptor. Here is the macrocycle, just like the things we've been looking at. Crown ethers, cryptans, things like that. Okay. The S, there's nothing very interesting, it's just a spacer. The F is a fluorophore, something that's fluorescent. Now, we said back in an earlier screencast that if a receptor changed its properties on binding, it could be a sensor. So, if the fluorophore changes its properties on metal binding, then this design can sense the substrate. The fluorescence changes. You can read out a fluorescence change very simply and can quantify it. How much of the metal do you have? So that's the basic principle. Bind a metal in here and hope the properties of the fluorophore change so that you can detect the metal that you've bound in here. Let's look at how AP brought that design to life with some real molecules. Here they are. So the first thing to say, we'll start on this molecule on the left, is we have just a polymer. He attached his molecule to a polymer support. Here, this unit is fluorescent. Okay? This unit is his spacer. And here we have essentially a 15 crown 5 with one of the oxygens changed for a nitrogen. What does 15 crown 5 want to bind? We've talked about it already. Sodium cations. It binds the sodium in here, it changes the fluorescence here, you get a readout, you detect how much sodium. Next molecule also has a polymer, also has a fluorescent bit. This time we have a larger macrocycle. What does it bind? Potassium. We know that larger macrocycles will go for potassium rather than sodium. So, detecting sodium, detecting potassium. Finally, same design, polymer, fluorophore. But this time, his ligand unit here is anionic. 2 negative charges. So it will bind a more charged cation. And it detects calcium really well. What do you need for blood electrolyte detection? Sodium, potassium, and calcium all tell you a lot about cardiac health, nervous system health, and so on. And he could detect with these 3 different receptors each of those different things. He put them onto a chip. You can see there are 5 detection units in this chip. The blood goes in here, flows through, and you detect with fluorescence of each of those a different analyte. And what this chip senses is, of course, sodium, potassium, calcium. It also happens to do acidity and oxygen levels. Everything you would want for rapid assessment of blood and health in blood. So he built this device. This is a device for instant blood electrolyte sensing. It is super low cost compared to what was being done for blood electrolyte sensing. It dropped the cost dramatically. And what he did is he put this and got this into ambulances in the developing world. This is a way that a low-cost ambulance service can detect blood electrolytes easily and simply. So particularly in India and Sri Lanka, in ambulances in developing world, there is a wide uptake of this type of technology for rapid blood analysis while the patient's on the way to hospital. So by the time the patient arrives, sometimes from a rural, very isolated area, they can say, these are the sodium, potassium, calcium, proton and oxygen levels that the patient has. And it's done for an absolute fraction of the cost of the equivalent equipment in a UK ambulance. So for me, it's a brilliant example of how you can take the basic principles of selective cation binding, hook it up to a detection system, and make a real device that can transform real people's lives with supramolecular chemistry.